Hello everyone, welcome to Calc Lesson number 43. Today we're going to be doing our fifth and final day of optimization notes. Okay, just two examples today. So starting with number 1, it says an indoor physical fitness room consists of a rectangular region with semicircles on each end. If the perimeter of the room is to be a 200-meter running track, find the dimensions that will make the area of the rectangular region as large as possible. So let's start with a picture. We need a rectangular region with semicircles on each end. So we need a rectangle and then these half circles on each end. So it kind of looks like a track. So we want to talk about the perimeter of the room, which is going to be a 200-meter running track. So I know the perimeter is going to be 200 meters. And then we eventually want to find the dimensions that are going to make the area of the rectangular region as large as possible. So we want to maximize this area here. So in order to do this, let's start by labeling our pieces. So I'm going to label my rectangle as X and Y. So to talk about the perimeter, I want to talk about the outside. So I definitely need those two X's, but I also need a way to account for these two semicircles. So let's think about the circumference of a circle. So the circumference of a circle would be 2 pi r. We have two semicircles, which is the same as one whole circle. So for each of these, we need to find that radius. So if this vertical distance is y, then the radius would be 1/2 y. So to account for both semicircles, the circumference of that whole circle would be 2 times pi times 1/2 y is the radius. So the circumference of that whole circle would just be pi y. So going back to our perimeter, we already counted for these two x's, but then to count for these two half circles or the full circle, it would be plus pi y. Okay, so we have the perimeter equation, and they're telling us that that's equal to 200. So let's take 2x plus pi y and set it equal to 200. Now we have an equation with two variables. Because we have two variables, we need a second equation. So let's look at what we want to actually find. We want to maximize the area of the rectangular region, so just this inside part. So we're looking to maximize area of that rectangle, which is just xy. Now we have two equations with two variables, so just like we were doing previously, we're going to solve our first equation for one variable and then plug it in. So let's take our perimeter equation and just solve it for y. So moving our 2x over, we have pi y equals 200 minus 2x. So y is equal to 200 minus 2x over pi. And now we can go ahead and plug that into our area equation. So we have area is equal to x times 200 minus 2x over pi. Let's distribute our x and break this into two fractions. So we have area equals 200 over pi times x minus 2 over pi x squared. Breaking it up was a good idea because now it'll be a little bit easier for us to take our derivative. So taking our derivative a prime, power rule just gives us 200 over pi minus, bringing our 2 in front, we get 4 over pi x to the first power. Now that we have that derivative, we can go ahead and set it equal to 0. So 200 over pi minus 4 over pi x equals 0. So we get 200 over pi equals 4 over pi x. Multiplying by pi over 4, so 200 over pi times pi over 4 will give us x. Our pi's are going to cancel, and we are just left with x equals 200 over 4, which is 50. We want to give both dimensions, so from there we can go ahead and plug 50 into our equation for y. So y equals 200 minus 2 times 50 over pi, so y is just 100 over pi. So finally, we want to give our dimensions. So the dimensions that are going to maximize the area of the rectangular region would be 50 meters times 100 over pi meters. Okay, our second one is a little bit different. This one says find the area of the largest rectangle that can be inscribed in a right triangle with legs of lengths 3 centimeters and 4 centimeters if two sides of the rectangle lie along the legs. So we really have to start with a picture. So the first thing they're telling us is that we have a right triangle with legs lengths of 4 centimeters and 3 centimeters. So let's draw a right triangle. And I'm going to label one side as 3 centimeters and one side as 4 centimeters. Now what we want is a rectangle that's inscribed in this triangle where two sides lie along the legs. So that means we're going to put a side here and a side here. And we don't know exactly where it's going to connect. But that's what we want to figure out is what the dimensions have to be to make that the largest area. So because we don't know the lengths, I'm going to label these as X and these as Y. Now I have two variables there, and I'm looking to maximize the area. So the inside, so the equation we're going to want to maximize is that X and Y. Two variables, which means I need a second equation. So in order to do this, I'm going to actually try to think through similar triangles. So I'm going to start with my large triangle that they told us. That's a right triangle that's 3 centimeters by 4 centimeters. And I'm going to compare that to this small similar triangle. So they share this corner angle and they both have that right angle. So that small triangle. Now the vertical side here is Y. To find the horizontal distance, we would have to take this 3 from our whole big triangle and subtract whatever our X distance is here. So this horizontal would be 3 minus X. So now we have two similar triangles that we can go ahead and set up a ratio to compare. So I'm going to set up a ratio of my first triangle as 4 over 3 and set that equal to the ratio of my second triangle as Y over 3 minus X. And now I can cross multiply to solve. So I have 3Y equals 4 times 3 minus X. So 3y equals 12 minus 4x. And I'm going to go ahead and solve this one for y so we can plug it back into our area equation. So y equals 12 divided by 3 is 4 minus 4/3 x. So now we have something that we can plug in for y. So we have our area equals x times, let's plug in what we found as y, 4 minus 4/3 x, and then distribute our x. So we have area equals 4x minus 4/3 x squared. So there's the area equation that we want to maximize. To do that, we're going to go ahead and take the derivative. So I'm actually going to jump over here. So a prime is equal to, using our power rule, we get 4 minus, bringing that 2 down, we get 8/3 x to the first power. And then we can go ahead and set this equal to 0. So we have 4 equals 8/3 x, multiplying by 3/8 on both sides. We get x equals 3 over 2. Then we can plug that into our y equation. So y equals 4 minus 4/3 times x, which we found as 3 over 2. 3's cancel, which is nice. So we get y equals 4 minus 2. So y equals 2. So we found those two dimensions, and then let's just go back to what it was asking us. Our goal is to find the area, so our area is just x times y. So area would be 3/2 times 2. So the area of our triangle, or of our rectangle, the largest possible rectangle inscribed in this right triangle, would be 3 centimeters squared. Okay, great job with these. You can now go ahead and try the problems in the homework 43 in the optimization homework packet. If you have any questions, you can ask your teacher.